basically we will talk about parabolic arches, but what we present can be extended to any arch in this geometry, in the, with this coordinates, which is described by an equation, parametric, an explicit equation of the axis line, y as a function of z. So, what do we need to do at first? We need to convert, transform our basic equations to account for change variables and to assume z as the order variable instead of s, that is along the beam axis. For doing this, we initially have to introduce some geometric preliminaries, so we have to switch from S to Z. And so we will start by computing the relationship between the ds and the z. ds, if is just given by the square root of the zeta squared plus the y squared. And since we have that y is equal to a function of z, we can write this as a 1 plus epsilon prime, y prime squared over the z. So this is, if you want, I can put brackets here to make it clear that I'm taking the square of the first derivative of y with respect to z. So from this relation, we obtain that the s over the zeta or the zeta over the s, in particular the zeta over the s, is equal to 1 over square root of 1 plus u prime squared. And this is an important relationship that we will use in short several times. Correct. Okay. So now, having this relationship, we can also compute other geometric quantities. In particular, we can use we can introduce this angle, the angle psi. The angle which is formed by the tangent to the beam axis with the horizontal line. So if we call this angle psi, what we can see easily is that sine of psi is equal to, if we take the sine, is the y over the s. And the y of the s can be computed simply as y prime the z over the s. Why? This is sine of psi. Then for cosine of psi is simply the z over the s. If we want to compute the tangent vector and radius or curvature, which we will not use very intensively afterward, but it can be useful to compute also those quantities. So if you want to compute A3 as the derivative of the position vector, today I will use the subscript to mean bold. The bold subscript it means bold letter, just because I'm using this tablet. So dx of dx over ds, we can compute this as by since x, the vector x, can be written as y I2 plus z I3 with the notation of the figure. So we are using these Cartesian coordinates y and z, the unit vectors we named I2 and I3. By computing this derivative, we obtain that this is equal to y prime I2 plus I3, simply, times the z over ds, which I will not expand, but is given here. So I think I should write this equation a little bit better, because I don't like the way it looks.
Un secondo.
Okay, so this will be used frequently, this quantity. So E3 is equal to this expression. And what about rho? 1 over rho, which is the curvature, is, as we know, is the derivative of the E3 with respect to the S. But we can use the chain rule to compute this quantity as dE3 over the z times the z over ds. And so by computing this derivative that are more easy to compute, we can finally obtain this expression that is given here. Is a bit cumbersome. Y second times 1 plus u prime squared, and all this quantity is over 3 over 2. So this is also the expression, the curvature, which we will not use very often, but it can be important to have this expression for other purposes beyond the ones that we will see later in this lecture. So again, I have at this point there is also tangent of C. Okay, tangent of C. I want if I also want to compute tangent of C, is simply u prime, by taking the ratio of sine divided cosine plus psi. Now to change, to scroll up, scroll down.
Due dita. So un dito è la stessa cosa.
So I can move back and forth. This is bothers me. How do I kill this?
Un dito verso l'alto.
Okay. So now, with these geometric preliminaries, we have to rewrite the equations, equilibrium equations, and compatibility and constitutive equations in these new coordinates. And so I will simply write this result. It will be not difficult to see that the equilibrium equations can be written as it follows: the T shear force over dz, that z. We should take the T over ds, but we take the T over applying the chain rule, the T over the z cosine of psi, plus n over rho, plus QR. QR is the radial load. This should be 0. We will use horizontal and vertical loads in short. Then the n over the z times cosine of psi minus t over rho. These were just the n over the s, but we are using this transformation formula that we have presented, minus t over rho plus qt.
No, seleziono delle cose.
Okay. Qt equal to 0, and the m over the z cosine of psi minus T plus CB, which are the distributed couples, equal to 0. Regarding QR and QT, since we are using these coordinates Y and Z, it's more convenient to relate QR and QT to horizontal and vertical distributions of load, and we will assume so. Then we draw the arch, and we can introduce vertical and horizontal distribution of load, or which will be referred to the unit length of the horizontal projection of the arch or in the vertical projection of the arch. With these new quantities, which are QB and QH, we can write that QT to be replaced in this formula is simply accounting also for the change of parametrization of the length over which those distributions are, or low distributions are referred. This will be QH sin psi cosine psi, because we have a projection of the load, and we also have to transform from dz to ds. So there is this double product of sine and cosine, and then there is plus QB sin psi cosine psi. And for the this is for the tangential load. For the radial load, we can write minus QH sine squared of psi plus QB cosine squared of psi. Okay, so these are the equilibrium equations. The other equations that we need to use are the other equations that we need to use are compatibility equations and constitutive equations. So we can use these equations together, and so we can write the compatibility and constitutive equation and as follows. So gamma, which is the shear strain, is dVr over the z cosine psi plus Vt tangent displacement over rho plus P, because we don't have derivative here, which is the rotation or the cross section. This will be T rho T over GA. So these are compatibility and constitutive equations. Together we are assuming 0 eigenstrains for simplicity. Epsilon, the axial strain, is equal to dVt over dz cosine C minus V rho over rho, and this is equal to the reduced axial force divided EA, which is N minus M over rho. Finally, theta, which is the bending strain, is equal to the phi over the z cosine of C, and it will be equal to M over E J rho minus and R, the reduced axial force, times rho E. Okay? So these are the equations, the set of equations that we should use. Now, we will use in short these equations, in particular we will use a simplification of these equations for small curvature of the beam axis. But it is important at this point to introduce the concept of funicular curve of what is the funicular curve or funicular shape of the arch for a given distribution if we assume in presence of pure vertical loading. So we are assuming QH equal to 0. We can introduce the concept of funicular curve. So what we will do, we want to have an arch that is shaped in such a way that it carries only axial forces and no shear forces and bending moments. So what we want is an arch that, if we take an element of the arch, we want the presence of only an axial force that we will assume positive in compression. This is the horizontal projection. We take infinitesimal, that's it. And this we will now project this axial. We want this to be the only stress to be present in the arch. So this an arch that is shaped this way is will be called as an arch with a funicular shape, because this can be taken, this shape can be taken. Obviously, the arch is subject to vertical loading. Why we name this funicular curve? Because if we revert the loading, we can find that this shape is the shape that is assumed by a chord, which is subject to the same loading, and so by inverting the shape of this cord, this rope, we will obtain the funicular curve of an arch that carries a vertical load. So we want only N to be present, and we introduce the horizontal HV component. Okay, now for be more, let's assume that this is not no. Let's go back to this color. This is no. Okay, I think okay. So let's assume that also at the two ends of this segment, N is not horizontal to not draw a degenerate case, a limit case, a special case. So in this force would be here we will have N plus the N, and here we will have the horizontal and vertical components that are H plus dH and V plus dV. So now what we will see is that what we want to see is that we want to write the equilibrium equations of the arch in this element of arch. Okay, so we want to have the horizontal and the vertical equilibrium. So if we will, for equilibrium, due to equilibrium of this free body diagram, we have that minus dV simply is a simple task to verify that we should have minus dV plus QV, that's it, equal to 0, and dh equal to 0. So h is constant. H will be the will be named horizontal thrust. I think is there is not an error here, but anyway, so there is one extra H here. I don't know to what might be not. Anyway, so this is not important, but what is important is that yes, there is this this H is missing. This thrust is okay, which in Italian would be la spinta. So this H is constant. On the other hand, we see simply that dy is equal dy over dz is equal by geometry. Dy over dz is simply equal to v over h by geometry, because v is basically is a line with the y direct axis and h with the horizontal axis. So we finally obtain, by taking the second derivative of this equation, the 2y over dz squared is equal, h is constant, so 1 over h, the v over dz, which is qb, is simply qb. Is simply qb. So this is the differential equation of the funicular curve. And now we can integrate this equation, and requiring that this curve passes through three points, because this will give us the needed integration constants. So we can impose this curve passes, we can integrate this equation, and so we will have, if now, but in order to make this integration, let us assume that qb is equal to q0 is equal to a constant. So we assume now that the vertical load is uniformly distributed along the horizontal projection of the arch. So in this case, it's a simple task to integrate this differential equation of the funicular curve or thrust line. We can integrate this equation, and we obtain the expression of a parabola, which is q0 over 2h zeta squared plus c1 plus c2. This is if we require that now we are using this system, and then the L, we have the span goes from A, and A is equal to 2A. Okay, so no. Okay, and this is L. So we have to require that y to minus for z equal to minus A is equal to a given value, fa, y to z equal to plus a is equal to another value of b. This could be also different, but we are we are referring to this special case in which a and b are equal to L over a is equal to L over 2, and finally y of 0 is 0. With this condition, we can obtain that the expression of the curve is 4f. F is the value at the vertex. 4f over L squared zeta squared. And there is also, because the y, we need 3 points, because we have C1, C2, and also H is a constant. And we obtain that H is equal to Q0. So Q0, this is important, L squared over 8F. So this is the funicular curve of the special case of uniform vertical loading per unit length of the horizontal projection of the arch. Now, this load distribution does not exactly correspond to several technical meaning loading distribution. For example, the self-weight is not vertical load per uniform vertical load per unit horizontal projection, because the self-weight is uniformly distributed. If we have, for example, a constant cross-section, is uniformly distributed over the arc length and not the horizontal projection. But for beams with a small curvature, for beams also that have either if we have a beam that has some properties like special geometric properties that I have listed here. Fine. Yes. So when the arch has a small rise, when f is much lower than L, arco ribassato in Italian would be the arch with a low rise arch. In this case, we can neglect the variation, that we can approximate the self-weight with a uniform load per unit horizontal projection. And also in other cases, if this vertical load is not the self-weight, is the weight of a filling that covers the arch, this loading condition may have a technical meaning. But so, in the end, why do we use parabolic arches? We use parabolic arches because they have funicular shape for uniformly distributed vertical loads. But so this is a general result. So for a parabolic arch, we should, in most cases, we have we assume this shape. Okay, where basically H and F are related to this second equation. But the question arises now when the arch is not statically determinate. So if the arch is statically determinate, isostatico in Italian, we give to the arch, we give this shape to the arch, and everything is fine. But so we have only axial faults. We have only axial faults. On the other hand, when the arch is not statically determinate, the value of H will be determined through the elastic problem of the arch. And due to the deformability of the axis line, the axial deformability, and maybe also the shear deformability of the arch, we can have that the value of h does not correspond to this value. So if we give the geometry, we have that the value of h does not correspond, which is solution of the elastic problem, does not correspond to this value here obtained here, to pure static equilibrium equations. And so we will have some bending moment. We will have some bending moment in the arch, not only axial force. But on the other hand, these bending moments may be of secondary importance, not relevant. For example, when the axial deformability is very low, and also the shear deformability is very low, as we will see now in one example. So this is the general framework, and now we discuss one numerical example, and we deal with a statically indeterminate example. So we have a parabolic arch which has two hinges and is subject to a uniform distribution of vertical load per unit length of the horizontal projection. Now, QV equal to Q0 because it's constant. And we are assuming these coordinates here, y and z. Okay, so we can name the two ends as A and B. And this structure is statically indeterminate, and so we need a way. We can solve the elastic problem. We can integrate the differential equation of equilibrium and compatibility equations, but this will be rather cumbersome. So what we do is we use actually I don't know the name of method in English at the moment. I cannot remember. We use this solution method based on introducing. This is our arch. We will introduce a statically determinate system, which is just a fixtures structure subject to the vertical load, same load, obviously, and also to an axial thrust that we will name x1, which is unknown. Okay, and we will determine the solution value of this quantity x1 through a compatibility equation which requires that this system is equivalent to the former one. This is S prime, this is S. We want that S prime is equivalent to S, so the compatibility equation is WB equal to 0, obviously. Okay? And now we want to apply we need to compute WB, and for doing this we use the principle of virtual work. So the principle of virtual work is obtained by taking in two ways, because we can have S prime divided into subsystems. So we will have S prime 0, which is subject only to Q0. And this is S prime 0. And then we have S prime 1, which is the arch loaded by only x1 by x1 equal to 1. Now, it's a simple task to obtain the forces in these systems. For example, in this system, obviously the two vertical reactions are Q0L over 2, Q0L over 2. If we want to compute the moment in the first bending moment distribution, we will have M0. I don't want to. So this just want to make sure that I write I wrote it here. Okay. Right equation. We can do it very simply, but I just want to make sure that I obtain the right that I'm not making any wrong computation. So this will be okay. So let's compute by ourselves, and then we compare with the exact solution. This is Z generic point, and this is L minus Z. So we have Q0 L over 2 Z, and we have the contribution of the distributed load will be over this part minus Q0 Z squared over 2. And so this can be written as Q0 Z over 2 times L minus Z. Okay. While in this other scheme, S prime 1, it's even simpler because we have that there is just an horizontal reaction equal to 1 on the other side, and so we can have here very simply that I will since this is the generic section, this is what we call psi. So it's a simple task to verify that in this system we have n1 equal to cosine of psi, because we have this force, the horizontal, we take in the generic section, we can do this, we take here infinitesimal element, we have this force 1, and this can be we have a normal force and the shear force, and since this is psi, n will be cosine, and this is 1, this will be cosine over psi, t1 will be minus sine of psi, because we have the two forces. We are assuming that the axial load is positive in compression, and then 1 is simply equal to minus y, because the eccentricity of this is simply y. So now we apply the principal virtual work to obtain WB, the two contribution of WB over these two subsystems. And so we obtain, these are, A, B, A, B. So now, if we want WB on the zero system, we apply the principal virtual work by taking, these are the stresses on the first scheme as the stress field, and the virtual displacement, we take those of the zero scheme. So by letting the force of this scheme to work for the displacement and deformations of the other scheme, we have 1 times WB0 here is equal to the integral from over the axis line over alpha. I will write this way, or alpha of the, this is what I should write. I should write N1 times the axial strain on the zero system, so N0 over EA. Let's remember that the constitutive equations are these ones. Epsilon is equal to NR over EA. So here I have to write R0 over EA plus T1, and here I have to write T rho T0 over GA plus M1 times M0, this I should write times, exactly, I should write M0 divided EG rho minus NR0 over EA. And this has to be integrated along the axis line. In this way, I obtain the first term of the compatibility equation. With WB equal to 0, we have a WB0 plus X1 WB1 equal to 0. If I want to compute the second term, WB1, I have to assume N1, and then I have simply to write, in this case, I have to take the stress on this scheme and the strain on the same scheme. So I obtain N1 over NR1 A plus T1 T rho T1 over GA plus M1 times M1 EG rho minus NR1 EA. This is yes. Now, okay, and we can carry the compatibility equation will be WB0 plus X1 WB1 equal to 0, from which we obtain the thrust in the solution value of the thrust force, which will be minus WB0 over WB1. Now, if we make the assumption that the beam is, for getting some reasonable result, we introduce the assumption of weak curvature beam at arch. Let's assume this assumption for obtaining some simple results. In this case, we can assume that NR is equal to N, essentially. Jr is equal to J, the AI, the standard moment of inertia, and Kr is equal to K. T rho is equal to K. In addition, we also introduce the assumptions that EA goes to infinity and also GA goes to infinity. So if we assume that the axial deformability and the shear deformability, no, we assume only GA. Let's assume only at first, let's assume only GA, but it goes to infinity. Yes. No, assume both, yeah, for obtaining these numbers, I think we assume both. Okay. We first have, because I will give you the final results that I'm taking from a reference, because it's a pretty cumbersome computation. If we only assume the GA going to infinity, at first, I will give you the value. So in this assumption, I will give you the result, the final result. X1 is equal to this value, Q0, L to the third power, 15 E I0. So there is also an assumption that I is equal to, we have also to simplify the computation, we can assume otherwise the I is equal to I0 cosine of psi, and I is equal to I0 divided cosine of psi. We are assuming this equation is to simplify the computations, and since you know there are cosine and there are of psi due to the expression of n1. This will make our life easier. And this assumption means that we are assuming that the arch has not a uniform cross-section, has a variable cross-section with I0 and I0 defining the keystone property, moment of inertia, and the area, cross-section area of the arch. So we are assuming the arch has not a uniform cross-section. With these assumptions, the expression of x1 is relatively simple, and this is Q0 F L squared divided 1 8 F squared L over 15 E I naught plus 1 over E I naught. So what we observe from here, that as we mentioned before, if E0 is not infinity and is not an infinitely large value, this x1 will be different from the value that we are obtaining for the funicular curve, which was written here. Written Q0 L squared over 8F. So this curve that was given a funicular shape, we are giving a funicular shape, has the axial thrust does not correspond to the value that gives zero bending moment. But if we can also find we can find a shortcut to overcome. So, but this difference will be not particularly relevant if e at 0 goes to infinity. In this case, this term goes to 0, and if this term 1 over e at 0 goes to 0, you will find that x1 is equal to 0 L squared 8f exactly, and so we will have that the funicular, the axis line is a funicular curve. While if there is an axial deformability of the axis line, this is not true. But we can also solve the problem in another way, and so we can also add to the arch a chain, an horizontal chain here, which has DC, AC. So to eliminate the truss, the horizontal truss, if we have this arch here, this being QV equal to Q naught. The solution, I will not go through the details, but we can modify we can just adapt the results, generalize the results that we obtained so far, and we will find that x1 is equal to this value, q0 f l to the third power 15e 0. 1 divided 8 f squared l over 15a by 0 plus 1 over 8 by 0. It's very simple to understand. We'll have an additional term plus 1 over EAC. So what we can do now? So we can correct the axis line if we apply a shortening to the chain, which is such that the shortening is such that delta G is equal to minus E at 0 plus 1 over EC. And see, so if we do this trick, we will eliminate we will have a coincidence of the axis line with the truss line. And so this concludes my presentation of this example, these two examples, the arch with the chain and without the chain, conclude my presentation of numerical examples relative to parabolic arches, by also having also introduced the concept of a funicular line. And I guess obviously we can have other loading condition. We can account for the curvature. We can get more accurate results for beams with a not weak curvature, and by using the equations, the exact equations that I provided at the beginning. So now I think that we can have a little break. I don't have the time, so yeah, it's about 1 hour from the beginning. I think we can what time is it now? I think we can meet at 4. 4:15. 4:15 in to continue with some applications on circular arches. Okay. Thank you. See you in 10 minutes.